So we have now a theorem about the properties of the transpose. So here A and B are matrices of the appropriate sizes, and K is a scalar. The first property here, A, is that if you take the transpose of the transpose, you get back itself. That makes sense when you think of the matrices visually and what the transpose does. It exchanges the rows and the columns. Well, if you first exchange the rows and the columns and then you exchange them back, you get back the original matrix. And if you run through the definitions of what happens on both sides of the equations for B and C, it basically falls out. You can see the book for more details on these. And E, one can show, follows pretty readily from D. So I'm just going to go ahead and prove D, because to me, that's the most interesting one. And it's also the weirdest one, because notice here, this change in the order. So A times B transpose is B transpose times A transpose. It is not A transpose B transpose. So let's go ahead and prove this. Proof of D. So let's suppose that A is, say, m by n, and B is n by r. Then A times B, which is an m by r matrix, when I take its transpose, I get an r by m matrix, and the same for B transpose times A transpose. This is because B, being an n by r, B transpose is r by n, and A transpose is n by m. So B transpose times A transpose is r by m also. So we know the two matrices are the same size, and so that all that's left to do is check to make sure the two have the same entries. So let's look. Well, the ij entry of AB transpose, well, by definition, that's a B J I. This is by definition. No, that's a T. And, well, using the definition of matrix multiplication, this is, I'll write it as row, this is not standard notation, but this is the jth row of A dotted with the ith column of B. But the jth row of A is the jth column of A transpose by definition, and the ith column of B is the ith row of B transpose, again by definition. Now let's rewrite this order so that we have it as we usually do. So we usually write the row first, then the column. So this is row I of B transpose dotted with column J of A transpose, which by definition is the ij entry of B transpose times A transpose. And so we've proved that this matrix here and this matrix here have the same entries, so therefore they must be equal. And now we put a tombstone, that's what this little thingy is called, because we just killed the proof. Yeah. Something to note, parts B and D extend to several matrices. So for instance, A plus B plus C transpose, that's A plus B plus C transpose. And so using part B, so this equals by part B, A plus B transpose plus C transpose. And then using part B again, this is A transpose plus B transpose plus C transpose. And similarly, A, B, C transpose, well, I can write this as A, B times C transpose. Then by part D of the theorem, this is C transpose times AB transpose. Again, pay attention to the change in the order. Applying part D again, this is C transpose times B transpose times A transpose.